There we go. So good afternoon, everyone. And I'll take this off so you can have a better chance of hearing me. Good afternoon, everyone. Welcome here in the physics building, and also to those of you online. It's my pleasure to introduce today Professor Tim Woollings from the Department of Physics at the University of Oxford. Professor Woollings was a trainee at Reading University, where he did his PhD and postdoc, and then in 2013 he moved to a lectureship at Oxford University, and he's a member of the Atmosphere, Ocean, and Planetary Physics subdepartment of the Department of Physics. And that's kind of a sister department to ours, I think, because there aren't many places in the world where we can do our kind of atmospheric science and our atmospheric physics within a physics department. And so that's a special feature for me to point out. So Tim's work, it will be presented today, is really on the atmospheric dynamics on the large scale, with a lot of focus on the extratropical circulation, the circulation outside the tropics, and how tropical dynamics influences extratropical dynamics. He's written a lot about blocking events and generators of extreme weather in our latitudes, and he's summarized a lot of his interest in the circulation in this nice book here, which I have a copy on my tablet, The Jet Stream. You can't see, but I'm waving it around at people. And it's a book, a nice book for you to pick up if you're interested in learning a little bit more about the dynamics of our atmosphere, and it's quite approachable. I also want to mention he's a fellow of Pembroke College, and he shared with me this morning that he thought he was the first meteorologist at Pembroke College, but it turns out that there was somebody before him. That was Hadley. So he's the second meteorologist at Pembroke College, but it's really not bad, because over the span of a few centuries, I think it still counts as quite an honor. So I'd like to ask you to welcome Tim as he talks about the physics of polar weather patterns.
Great, brilliant. Thank you, Paul. Thank you. Yeah, I didn't mention earlier. So Hadley, when Hadley was at my college, he was actually a lawyer. And so in those days, a lot of science was like a hobby. And so his day job, I guess, was a lot more lucrative. He was a lawyer in London, doing a bit of meteorology and science on the side. But yeah, it's great. It's really nice to kind of come, at least virtually, to Toronto. Paul's right, it really feels like a kind of a sibling department, which is really nice. And it is great. We really benefit from being kind of within a physics environment, looking at kind of atmospheric problems. So yeah, what I'm going to talk about today is really something that kind of came out of a sabbatical I had a couple of years ago in Bergen in Norway. So it's kind of like there's a whole bunch of people here who have really contributed lots to this. It's essentially kind of a bunch of people from Oxford and a bunch from Bergen, and then a few kind of randoms in there. And yeah, this is I guess my sabbatical was in 2020, so this has all been kind of somewhat delayed with COVID and other things, but it's now basically out. So there's a preprint here at the moment in weather and climate dynamics, and I think I have like about 3 days left for the deadline to resubmit the revised version. So yeah, hopefully I'll make that. So yeah, this is really about the kind of the physics of large scale weather patterns, as Paul said. So what I'm going to do today, I'll start with some kind of motivation and some examples of the kind of events that I'm talking about and that I think are interesting. I'll talk quite a bit about Rossby waves. So these, for those who aren't familiar, Rossby waves are really kind of dominant. It's a really dominant structure of atmospheric variability in the mid-latitudes, right? So all of these things, all these kind of swirls and wavy patterns that you can see in this wind picture here, those are all Rossby waves in the mid-latitudes. So they're super dominant. They're like, you know, it's what you see when you look at any given day on a global scale. You see the Rossby waves. But a lot of this talk is kind of understanding how these things behave at high latitudes, which isn't super obvious. And then what that'll kind of blend into a bit of a picture of kind of, you know, how I think we should view polar dynamics. I think a lot of atmospheric dynamics you could describe as basically turbulence plus waves, and to kind of give away a little bit of the answer here, I'm going to suggest ultimately the polar regions, we just have a kind of a slightly different balance between these two things, as we do in mid-latitudes. And then right at the end, I'm going to talk a little bit, if I haven't run out of time, about kind of whether you can actually force these waves from the polar regions. But I'll get onto that in a minute. So please do kind of interrupt as I go along. I'm very happy to take questions. I can't see anything at the moment apart from my slides and me, which is slightly bizarre. But yeah, Paul or anyone else, please just shout, and I'm happy to take questions whenever. Okay, so some of the motivation, I guess, for this was we have a lot of probably a lot of confusion, I'd say, still, both in the science and kind of in the media and outside the science, over events like this. Right, this was an event last year when people in Texas were kind of slightly surprised to find it looking a bit more like Toronto than Texas, maybe. And what happened here was we had a really kind of, large kind of spilling of cold air down over North America as part of this wave pattern. This is one of these Rossby waves. And so this kind of debate, this kind of event has spurred lots of debate about how Rossby waves, how they can be influenced by the Arctic. So I kind of set out to investigate this, and what I've ended up doing is actually a lot more just kind of understanding the Arctic itself in its own right, not so much kind of how it impacts Texas, for example. But there is one kind of really specific thing that I will try and talk about at the end, as I said, and this is a kind of a really specific theory that's had a lot of attention, and there's quite a bit of evidence for it, that sea ice up here in this region, kind of north of Eurasia, the loss of sea ice there as the climate has warmed seems to have kind of triggered one of these atmospheric Rossby waves that's come down to lower latitudes, and we had a really kind of anomalous cooling trend here over Central Asia over the last, well, I guess kind of about a decade ago now. And so there was lots of interest here in, why is this region cooling while the rest of the world is warming? Is it a response of the atmosphere to the heating over the Arctic as the ice is lost? So right at the end, I'll try and connect back to this and see whether we think that you can trigger waves like this from the Arctic. A couple of kind of prettier pictures of interesting events. Back in 2020, we had a really kind of a really horrible period of wildfires in Siberia, and this was a very large region. It was essentially associated with a really kind of persistent weather pattern. So we had this weather system that kind of hung around over Siberia. It drifted gradually towards the west over the period of kind of several weeks. And one of the things that this weather system did is it pulled up a lot of kind of warm and dry air from further south on the continent, and that really helped to kind of fuel the wildfires. So one thing we're going to try and learn about is these really kind of persistent weather systems that kind of gradually move across the high latitudes, and that's that kind of persistence is a key thing. I'll try and talk a little bit about Arctic cyclones as well as we go along. So this is a satellite picture. You can see Greenland over here, a kind of distinctive shape. And this is a huge cyclone kind of sat right over the North Pole and kind of really filling the Arctic basin here. There's a lot of interest in these cyclones because of their impact on the sea ice. So they do, just the winds do a lot of work in moving around the sea ice and breaking it up. And so, you know, as the ice kind of gets more fragile, it's a lot more vulnerable to these kind of systems. And again, the key thing with these is the persistence. So these kind of cyclones last quite a bit longer than we expect, you know, based on the kind of cyclones that at least that we get in the UK, and I think you can probably get in Canada as well. So that's the key thing. That's one of the most concrete things I'll try and answer is why are events like these cyclones so persistent? Right, so let's move on to introduce Rossby waves. This is Rossby. He was a kind of a Swedish American meteorologist who did a lot of great work. Well, during the Second World War and afterwards. I think he was certainly the first meteorologist to get onto the cover of Time. I don't know if there have been any others since. But he's given his name to these waves, right? And he was a real kind of mix of a theoretician. A lot of the theories that we use for these essentially come from Rossby, but he was also really into observations. And it was really during and after the war that they set up these big observational networks and actually managed to detect these huge waves that go around the whole kind of hemisphere that no one had really kind of been able to measure before. So this map that we're looking at here, you can think of these essentially as streamlines, so that the wind is blowing around parallel to the contours here. And we've got North America over here, and Asia over here. And so these are really kind of planetary scale meanders in the flow, right? So the jet stream is blowing around from west to east here, but it's not blowing straight, it's kind of meandering north and south. And so these meanders are what we call Rossby waves. This is a great paper, by the way. This is a real classic. It's a very modest paper because there are no authors. There's not like a list of authors. It's just listed as being kind of written by the staff members of I think the Chicago Meteorology Department. And it's obviously, it's obviously Rossby, but with a lot of his friends who put this thing together. So what is the basic mechanism for Rossby waves? So it essentially comes down to conservation of vorticity, right? So the vorticity, it's the, in fluid dynamics terms, it's the curl of the wind field. So it's a measure of the kind of local spin or the local rotation of a fluid parcel. And the really key thing is that a bit of air on Earth, so any bit of air somewhere on the surface here, that has kind of two contributions to its vorticity. It has one part because the bit of air, it might be spinning with respect to the ground. That's what I'll try to show here. But it's also got a component of vorticity because the planet itself is spinning about its axis, right? So this is the axis of the Earth here, with the North Pole up here. And so the Rossby waves kind of arise from like a trade-off between these two types of vorticity, essentially because the total vorticity is conserved. So the sum of the planetary part and the relative part. And what really matters after you do some kind of scale analysis and stuff, what really matters for the fluid parcel is the vorticity about its kind of local vertical, which is the dashed line there. So, for example, if we take this bit of air and we move it polewards, then you can kind of see that these two axes come closer together, right? And so the planetary axis is going to kind of project more onto the axis of our fluid parcel, and so for the fluid parcel, what that means is that its planetary vorticity increases. Okay, just because you've moved it north, but the total is conserved, and so in response, the relative vorticity has to decrease, and so that's what happens to this guy. He moves further poleward. His relative vorticity decreases, and that's essentially how we form an anticyclone. Right, so anticyclonic just means that the air is turning in the opposite direction to the rotation of the Earth. So we've created a weather system just by moving this air north. It could have been completely stationary here. It could have not have had any relative vorticity, but just moving it north, we've turned it into an anticyclone. And so there's a bit of a sketch here of kind of showing how things evolve after that. Now we're looking down on the kind of developing wave from above, so down the kind of local vertical axis. So if we imagine, let's say we've got the jet stream here, as we saw in Rossby's picture, we've got our bit of air and we've moved it north. So we just learned that forms our anticyclone. So there's some relative vorticity and the air is spinning in this direction. You can see how that's kind of disturbed the jet already. It's kind of shifted it a little bit north here. And essentially the impact of this vorticity anomaly on the surrounding air parcels is what helps to develop the wave. So if you think about what the influence of the dashed lines might be, you can see that our kind of bit of jet stream on this side is going to be pushed north, and the jet stream on this side is going to be pushed south by the winds. Essentially, you can invert the vorticity field to kind of infer a wind pattern, and that's what we're looking at here in the dashed lines. So what happens a little bit later then, if we've moved this bit of jet north and this bit of jet south, is we end up with a picture down here in number 3, where our original anticyclone has moved a little bit to the west. Okay, so it's moved to the left in this picture. And the kind of the wind blowing down here has actually created something new, right? We're starting to create a cyclone here, which is a new feature, right? We only had the anticyclone to start with, and now we're generating a cyclone as well. And then these things develop, right? Each of these anomalies will then affect the fluid around them, and pretty soon you have a wave pattern. And so this is this obviously has a phase velocity, right? So you can see our individual system is shifting upstream over time, so towards the west. But we've also generated new features. So we have in this case, we have an eastward group velocity, so in the other direction. So this is the kind of basic mechanism for a Rossby wave. But you can see that the really kind of key thing that this relies on is the fact that there's a north-south gradient in vorticity. Right, so the vorticity that we get from the planetary rotation, that's really large. Maybe if I go back up here, that's really large up here. But if you're down near the equator, that vorticity doesn't project onto your axis very much at all. So so the gradient here in planetary vorticity is what allows the waves to form. But the kind of interesting thing for us, if we think about the polar regions now, in the polar regions, we have a lot of planetary vorticity. It's really strong up here, but actually there's not much of a gradient here. The gradient's very strong down here, but there's not much of a gradient up here in the planetary vorticity. And so just based on this consideration, actually, we shouldn't really expect Rossby waves to be very prevalent in the polar regions, because there's not much of a vorticity gradient there. And so the way we tend to phrase this is the kind of beta effect. So we measure vorticity by the Coriolis parameter. You might have heard of the Coriolis force as being kind of a way of visualizing the effect of the rotation. And so if we just linearize the Coriolis parameter, then we have a constant term, and the kind of linear term in the Taylor expansion has a coefficient of beta. And beta is really measuring this gradient, the meridional gradient in the vorticity. So it's what we call the beta effect, which gives us the waves in mid-latitudes. And the key problem here is just that beta is small in the polar regions. Right, it goes like the cosine of the latitude, and so as your latitude gets closer to 90 degrees, then beta, or this vorticity gradient, is very weak. So how do the waves behave? Do we get waves? How important are they? Those are the kind of questions that we're looking at. And so this is kind of a way of quantifying a kind of potential for Rossby wave propagation on the kind of background state that we have. And so this is a little bit more complicated than just beta, because the waves propagate on a vorticity gradient. Beta measures the planetary vorticity gradient, but for the full picture, we also need to include the relative vorticity gradient. And so because we have kind of wind fields, we have kind of shear in the wind, that's essentially a vorticity, and in particular a vorticity gradient, which contributes to the kind of potential for Rossby waves. So we struggled a bit with the color bar on these things, as you can see, because we have very different numbers. But basically the kind of numbers that we're getting up here in this is the Barents-Kara Sea region, where we think we have these theories that the ice loss has triggered Rossby waves. You can see that we've just about got some potential here. This is about 20% of the strength of the mid-latitude gradients around here. So it's much weaker. And if we go just a little bit more into the Arctic and towards Siberia here, we have very, very low potential for wave propagation. So as we kind of suspected, we shouldn't really expect these waves to be contributing that much. So this is winter, December to February. June, July, August in the summer, we have a bit more. We have this kind of extra jet stream up here. So the temperature contrast between the warm Asian continent and the cold Arctic Ocean gives us like another little jet stream here, which acts as a relative vorticity gradient. And so actually one of our conclusions really is that it's not the winter season that's really so important here. It's the other seasons, particularly summer and autumn. You see quite a strong gradient up here, and that ties in with some of the theories that people have suggested, that it's some of these other seasons where we should expect to see the Rossby wave effects a bit more. So just a little bit of theory. I'm just going to outline. This is essentially the kind of simplest theory for Rossby waves. This is something we call the barotropic vorticity equation. So barotropic means that it's essentially just kind of one layer of fluid in this kind of simplified theory. And all we're doing is advecting vorticity around. So the vorticity here is advected by the winds U and V. So U is directed east, V is directed north, and we have our beta here, which is the meridional gradient in the vorticity. And beta star, the star just means that it does include the relative vorticity gradient here, as well as the planetary component. So it's a really simple vorticity equation. If you linearize it, so you look for kind of wave-like solutions in both the east-west direction. So K is our east-west wave number, L is our north-south wave number, and omega is our frequency. Then you can very easily get a dispersion relation here, which links your frequency with your wave numbers. So this is very nice. This is useful. From this, we can derive a phase velocity here. So just omega divided by K gives us our phase velocity, which is we have, so U is the kind of background wind field. So we saw those maps with the kind of the jet stream moving from west to east. This is kind of, in this simple case, this is assumed to be a uniform background wind field blowing from west to east. And so then we have we're subtracting off something positive then. So in terms of the phase speed, as we saw in the sketches, all these things are swimming upstream, right? The jet here is trying to blow them to the east, but the waves themselves, in terms of phase speed, they're swimming upstream against that flow. And we'll see this in some of the analysis in a bit. So you can also calculate group velocities. Obviously, if you do d omega dk and d omega dl, then this gives us the group velocity, right? So the velocity at which we think the energy will be propagating. And all we've done is just in this very simple theory is we've just kind of related the phase and the group velocities, right? So the group velocity actually you can write as the zonal phase velocity, right? This omega over k plus another term, all right? And so the other term, it depends on the wave number. It depends on alpha, which is the kind of the angle that the wave is propagating with respect to the east-west direction. But the key thing that we're going to highlight is the fact that it also depends on beta star. And so as we move to the higher latitudes where beta is small, then one thing that we should expect to see is that this term will get small, and our phase and our group velocities should become more similar. And so one of the kind of main things we're finding is really kind of a much reduced role for wave dispersion at high latitudes compared to the low latitudes. Right. I'm not going to go into details here, but I thought I'd just outline a few other bits of theory. It was quite fun. We spent some time just kind of revising some theory that's been used a lot at kind of lower latitudes, but hadn't really been thought about so much at high latitudes. And so a couple of things just to point out. So in general, we should expect kind of wave amplitude to increase at high latitudes, and also that only the kind of longer waves get to higher latitudes, the lower wave numbers. So this is from a real classic paper, Hoskins and Coriolis, and just some ray tracing experiments that they did. You can see that wave number 1 here gets up to the highest latitude, and then as you go to higher wave numbers, so to smaller scales, the amplitude drops off, and the waves don't get as far poleward. There's some more stuff down here. And so because we've got long waves at high latitudes, and we also have weak westerlies here. So in a more, our simple theory just now had a constant U, but in reality, we have weaker background flow at high latitudes. And so we should expect to actually see westward phase speeds. So we'll look out for that in a minute. And there's some, the kind of classic ray tracing makes a stationarity assumption in that the phase speed is 0. Yang and Hoskins kind of extended this to think about what happens when the phase velocity isn't 0. And essentially for these, for this case here, we're expecting our phase speed to be actually upstream, to be westward. Then we're expecting quite a meridional group velocity, right? So the group velocity is kind of oriented a bit north compared to our wave vector. So we're kind of expecting some of these kind of more meridional wave paths here. So I haven't kind of proved any of that. That's just a whistle stop tour of some theory. So what do we see in reality? What we've done in this bit of work is kind of a statistical analysis to identify wave structures in the atmosphere. And so we do this by a kind of a correlation analysis. What we're looking at here is, so we're looking at longitude on the x-axis and the lag in days on the y-axis. So time is moving down here. And to generate these plots, we essentially, we had a base point in the middle here, and we correlated all the other longitudes at different times with this base point. So if we got things right, there should be a 1, the value should be 1 in the middle here, and then it drops off to 0 out here. And so this kind of analysis, allows you to include lots and lots of different storms, lots of different eddies and things contributing to this. And so this is the real kind of classic evolution that we see in the mid-latitudes, right? So this one is from 45 degrees south. And we see really dispersive wave packets. Right, that's the kind of the main thing to point out. So so as time goes on, our individual peak here is drifting to the east. Right, so we have a phase velocity here, which is downstream. But then you can also see a group velocity, which is much faster. Right, so that's covering longitudes much more quickly. And so one of the really key things in the mid latitudes, actually, if this was a storm in the mid latitudes, then part of the way that decays is through wave dispersion, right? It's fluxing energy downstream, right? The wave packet is moving faster than the individual system, and so wave dispersion is a kind of a key mechanism for decay in the mid latitudes. If we go further poleward, so we're at 60 south, we can see that there is still some dispersion. It still looks a bit wave-like, but kind of less so, right? We've got much weaker features on either side here, to the west and to the east. We still have really clear phase propagation, and there is some group propagation here. So it's kind of still a little bit wave-like, but dispersion is obviously playing less of a role than it did in the mid-latitudes. And then if we go further poleward still, the whole picture kind of changes completely. Right, so suddenly it's not looking wave-like at all, really, at least at kind of first sight. So So all of our correlations are positive, right? There are no blue things on here. All the different longitudes, all the different times, it's all positive correlations, kind of, on average. And so, yeah, it's looking a lot less like a wave here, to be honest. But I think there is still some, there's still some propagation here, right? And you can tell that because you can see there's a little, there's a bit of a drift of our feature towards the west over time. And that's really interesting because even at these latitudes, the background wind is still westerly. So the wind is trying to push this thing towards the east. And so it is actually propagating upstream. We talked about the long waves at the high latitudes actually having a westward phase velocity. And so this thing, it doesn't really look wave-like, but it is still propagating. It's not just advecting, which is interesting. Bit of a more kind of local picture here. We're looking. This is an example from the northern hemisphere. This is at 65 north. We've kind of combined all the different longitudes in this. So this isn't just one location. This is kind of representative of an average behaviour all around the northern hemisphere. But we're these would be maps, right? If this was just at one location, these would be maps. The y-axis here is the latitude, and the x-axis is the longitude. But this is kind of relative to our base point. We're looking at the evolution over time, right? So there's a 2-day lag between each map. So lag 0, this is our base point. Again, we should have a 1 there if we've got everything right. And so you can see what structures correlate with this point in the days before and the days after our kind of base point. So there's a few things that we see here, which are hopefully kind of resonating a bit with the theory. We can see a kind of a gradual upstream drift of our main feature. So we have, again, we have westward phase velocity against the mean flow. There's some evidence for dispersion, and you can see a kind of a group velocity. I tried to kind of sketch here what might be a group velocity. It's definitely weaker than in the mid-latitudes. And it has quite a kind of a meridional path, which is one of the things we predicted from the theory. In the mid-latitudes, these things would go much more zonally. So overall, this kind of suggests that we do see some aspects of wave-like behaviour at the high latitudes, but it's certainly kind of weaker than in the mid-latitudes. Maybe I won't go into details of this looking at the time, but our theory essentially predicted that the phase and the group velocity would get more similar as you go to high latitudes. So the theory here, as we go south, this difference between the velocities should decrease, and this is observationally derived. So we can see that as we go towards the South Pole, in this case, our phase and our group velocities are coming closer together, and so there's less of an effect of dispersion. So I should kind of move on. So we found basically we've found some features of Rossby waves that are relevant at high latitudes, but they're definitely weaker than in mid latitudes. So what else is going on, right? There's obviously something else going on as well. And as I hinted before, what's going on is basically turbulence. So another great meteorologist here, Jules Charney, kind of pioneered the study of what we call geostrophic turbulence. So this is it's essentially like two-dimensional turbulence. so specifically, it's the so geostrophy is a kind of a very strong balance of terms in the fluids equations, and it's that geostrophic balance that is kind of inhibiting the inhibiting the cascades, and it's that specifically that kind of gives us this brand of turbulence. But yeah, if you think of it as kind of two-dimensional turbulence, you're not going too far wrong. So what Charney found, looking at a really small sample of atmospheric data from the 60s, he found a kind of a characteristic spectral slope in the atmospheric velocities. So U and V are the velocities here. And he had like a winter set of data and a summer set of data. And essentially for relatively high wave numbers, he identified this k to the -3 slope, which he derived from his kind of geostrophic theory. So this is representing a cascade of energy to large scales within the atmosphere. And within this range, where I've kind of highlighted in red, this k to the -3 slope, a key thing is that it's isotropic, right? So U is the east-west velocity, V is the north-south velocity, and these things are behaving really similarly, right? At least within this range. So this is isotropic turbulence. Of course, what happens then at larger scales is really kind of strikingly different. So as you go to the larger kind of really planetary scales here, then the energy in V really drops off. So you've still got a lot of energy in U, the dashed line. And so these are the jet streams and the kind of elongated features. And this was really, this was described really well and studied by Peter Rines, who essentially kind of, he kind of pioneered this view of the balance between, having a balance between waves and turbulence. So in, he did some numerical model simulations. First of all, with beta equal to 0, right? So there's no planetary vorticity gradient here at all. So this is like a cylindrical Earth or something. There's no vorticity gradient, and so time goes down here. That's the y-axis, and so you start off with kind of small eddies at this early time, and then the eddies are merging over time, as you might expect in 2D turbulence. And so as time goes on, you end up with much larger eddies, right? And so this is the energy cascade to large scales. But then what the beta effect does, so the fact that we're on a spherical Earth that's rotating, what happens is that these things grow over time. The eddies get larger, but they get to the point where Rossby wave propagation becomes really efficient, right? So the eddies get to the scale where they really feel the planetary rotation, and then they start to propagate instead. So instead of just carrying on merging and getting larger and larger, they propagate as waves, and so this is what is inhibiting that cascade that we just saw in the meridional direction. It's really the kind of the formation of Rossby waves due to the beta effect that causes that cascade to be stopped. So what happens in the polar regions then? So this is our version of the spectra. So we're looking at eddy kinetic energy spectra here. So we've combined all the different months. We removed the stationary waves, but otherwise this is just everything. There's no filtering or anything. So as a function of latitude and zonal wave number, how much kind of any kinetic energy is there in the atmosphere? You can see there's a lot of energy in mid-latitudes, and you can kind of see the flattening of the spectrum, right? So as we start at high wave numbers here and move to lower wave numbers, then we have our spectral slope here, right, the k⁻³ slope. But then the spectrum flattens. So as you go to lower and lower wave numbers here, it's not changing anymore. So the cascade has been inhibited here in the mid-latitudes. And there's a hint maybe that in the polar regions that's not quite the case so much. It seems like maybe it's not super clear from here, but I think the cascade goes a little bit further. But the key thing we found that's really different is the kind of isotropy of the eddies. So if we look at this quantity, sorry, my laser pointer is being a bit funny. If we take the difference between u² and v² rather than the sum of them, this is the kind of classical measure of eddy anisotropy. So where this is negative, like in the blue region, then our eddies are really kind of stretched out in the north-south direction like this. Where we've got positive values here, the eddies are stretched out in the east-west direction, like the jet streams and the very elongated waves. And so the point is that up in the polar region, there's a lot of energy here still from in the previous plot, but the value of this n metric is close to 0. So these eddies are much more circular as we go to the high latitudes. So it's really, they're really much more like kind of isotropic vortices. So this is kind of a summary, at least to the kind of the main point. So the atmosphere is basically, at least on these large scales, the atmosphere is waves plus turbulence. I think that's really well established. These things coexist, and basically how we should think about the polar regions is it's just a shift in the balance, right? The balance is shifted kind of more in favor of the turbulence, and kind of away from the Rossby waves, right? So just the kind of fraction of variance, more of it's in the vortices and less of it's in the waves. But we have still seen really kind of clear characteristics of waves, right? So the westward phase velocity, right? So this is like the Siberian event, right, where we had this kind of slow weather system drifting upstream, drifting to the west. That kind of westward phase velocity is really characteristic of Rossby wave propagation. And another really key thing is just the lack of wave dispersion, right? So we have more persistent systems at high latitudes, and that's partly. So I guess we talked about this cyclone here, this really long-lived cyclone. So partly it's we always, there's a tendency to say, oh, why did that last so long? What caused it to last so long? And one of the key things is just that it's lacking one of the two decay mechanisms that the other cyclones have in mid-latitudes. So if this guy was in mid-latitudes, there would be wave dispersion downstream, and that would contribute to the decay of the cyclone. You do also see, you also often see kind of cyclones merging in the Arctic. This is an example of, this is like kind of, these are like surface pressure traces following one kind of very persistent cyclone, with the suggestion that it was reinforced by other kind of vortices moving in and merging with it. And so this seems consistent with a kind of a more turbulent picture where we have vortices merging together. Right, I think I should probably stop here, but I'll so the final thing that we did, I guess the other bit of motivation I said was like, can we in this case here, can we really actually trigger Rossby waves from the Arctic, which might come down and affect the mid-latitudes? What we've done here is particularly look, the way these things often work is you have some local forcing, like the ice loss, and then typically there's like a local response, which is often, we can often kind of understand that pretty well using linear dynamics. And then this triggers some other response. In this case, we'll be looking for a Rossby wave. So without really going into details, again, this kind of classic paper from the 80s, we realized that they kind of tell us in great detail what happens in the tropics, and then even more detail what happens in the mid-latitudes, with two different types of it. But they don't talk at all about the polar regions. Right, so if you put in some anomalous heating at the surface, in the tropics, that's balanced by ascent, which gives you adiabatic cooling. In the mid-latitudes, you balance that heating by bringing colder air from further polewards. But in the Arctic, you can't, there's nowhere colder, right? So I think none of these things work in the polar regions. The stability is really high in the tropics, in the polar regions. You can't have this ascent. The temperature gradients are weak in the mid-latitudes, in the polar regions. So none of these mechanisms work. I won't go into the details here, but basically we think the response, this kind of local response to heating, is really what balances it in the linear dynamics. Is just the radiative damping. So you remove some sea ice, the air gets warmer, it gets less cold, maybe, let's say that. And what brings it back into balance is really just the radiative heat loss. And that forms this really characteristic baroclinic structure. Maybe this is the neatest thing to look at, where you have a cyclone at the surface and then quite a deep anticyclone above it. So it's almost, this is like a polar monsoon, really, which is quite a strange thing. But this does give us a big anomaly up here, which we think can then trigger Rossby waves. So as I expected, I didn't really have time to do that bit justice. But yeah, these are the conclusions. Basically, the polar regions, they just have a different balance, right? A bit more of the kind of isotropic turbulence and less wave activity than mid-latitudes. But we do have some vorticity gradients. We do see wave-like features up to about kind of 75 north or south, I'd say. And kind of Rossby wave effects, like the propagation, can explain some of these really high impact events that we've seen, as in the wildfires. As I said, dispersion is really kind of fundamental in mid-latitudes. But we don't see it in the polar regions, and yeah, you might have to take my word for it that we think waves can actually, even be forced from the polar regions, albeit quite weakly, and probably only really in summer and autumn. Okay, I'll stop there. Thanks very much.